gel cell batteries, all powered by this little solar panel right here. Very problematic, very testy systems that like to break the day after you make a site visit. So one of the things that I've done recently is to upgrade these sites to what is known as a pressure transducer technology. Now here's an example of one of these down here on the bottom. These are relatively small, generally less than 1 inch in diameter and probably between 6 and 8 inches long, depending on the manufacturer. Have a number of advantages over these old systems of gauging, including non-volatile memory, not worried about losing it if the power goes out, so to speak. A lot of them have multi-year batteries, which is great for installation in really remote locations where you won't be able to get back to them very often. There are no moving parts, there are no floats and counterweights, there are no exposed wires or things that can break or be eaten by squirrels. The easier data retrieval in the old section. I can just bring a PDA down into the field that has all the software necessary to download that and make changes to the data logger if needs be. Additionally, these sites have a much smaller footprint. Now, they can be installed in a much more inconspicuous location than you could be previously, where the entire system can be just set up in a little PVC or metal pipe in comparison to this whole setup that we had before. Now, as great as these are, you still have a lot of the same problems as you did with that old system, with still having channel changes over time and being able to get out to these sites often enough to build up a good rating curve. But it made my life a lot easier, and the technology is definitely a step in the right direction. So, what can we see with these data? Well, the output of these stage recorders is a hydrograph, which essentially tracks the stage of the spring over time. And we can see from that trends over time, seasonality of discharge, the response time to such things as precipitation events, as well as the behavior of the aquifer system that's supplying that spring. Now, continual monitoring is important, but so are manual measurements at the site. In order to convert these stage data into actual spring discharge data, you have to go out and make manual measurements of flow. So on this hydrograph here, the red arrows indicate when that site was actually visited and a manual measurement of spring discharge was made. From there, we can correspond that to the stage at that time, build up a curve that relates all of the other stage data into spring discharge, and then convert it to an actual volume over time rather than just a dimensionless number. Something else that we can look at with these hydrographs is its shape. And we can see on this is actually Roaring Springs, about 9 months worth of Roaring Springs data from a more recent NAU grad student studying in that area. And we can see that there's little to no response to monsoon precipitation events, but we have this massive response during this spring snowmelt season. Looking at the shape of that hydrograph, we can tease out a lot of information of what's going on within that system. Looking at the rising limb of that hydrograph peak, we can get an idea of how quickly that water is being taken from the rims as that snow melt and brought into the aquifer system to discharge at the spring. Looking at the recession curve, the back end of that peak, we can break it down into a number of different elements, such as a first high slope feature, which represents the drainage of the conduits and the fractures in that aquifer. Moving to a slightly less slope section representing the drainage of fractures and then the beginning of the aquifer matrix beginning to release its groundwater. And then finally a low slope line representing the drainage of the aquifer matrix back down to a base flow condition again. So at sites where we don't have these continual monitoring equipment, periodic monitoring still occurs, although many of these sites actually now are being logged for both air and water temperature. That technology has become so cheap and so easy to install in the field that I've been putting them out at a number of different locations, but I'm still calling these ungauged sites. And some of the other data that we collect are repeat photography, such as here at Cottonwood Creek, where the gauge flows nicely for part of the year and actually is completely dry for part of the year. Some of the output from these air and water temperature loggers can give us an idea of the stability of the aquifer system supplying the water, as well as when and if that spring goes dry for periods of time in the year, which we may or may not otherwise know just going to the site once or twice per year. Measurements of spring flow, either a volumetric measurement made at a low volume spring, perhaps using a flume for a little bit of a higher volume spring, or using a flow meter for a really high volume spring. Now you'll see that that photograph is pretty familiar from that LaRue 1920s photo. The technology for measuring spring discharge using a flow meter hasn't changed in almost a century. Now some of the other field parameters and things that we measure when going out include the measurement of temperature, both air and water, pH, electrical conductivity, dissolved oxygen, as well as geochemical data, some of which can be collected and analyzed in the field, but generally I'm talking about samples that are collected in the field and then brought back for laboratory analysis, including alkalinity, dissolved in constituents like nitrates and sulfates and phosphates, stable and radioactive isotopes. We can tell a lot about the springs and seeps and the aquifers that supply them from these isotopes. Major ions and metals, nutrients, trace elements, a huge list of things. Now what we can do with these data is develop spatial relations as well as trends over time for them. The graphs over here on the right, we have alkalinity on the top and pH on the bottom, just as an example of what we can look at with these data. Spatially, we're looking at a set of springs along the south rim from Hermit Creek on the west to Cottonwood Creek off of Horseshoe Mesa on the east. And so we can look at how these constituents vary within that site, but also tease out relationships and patterns spatially as well. Now, I'd like to use stable isotopes really quickly as just as an example of how spring chemistry can be used to infer groundwater behavior. Now, I won't go into the whole process of the kinetic fractionation of hydrogen and oxygen molecules or anything like that, but just to let you know that these elements behave in a predictable pattern and can give you information on such things as winter versus summer precipitation, or a high altitude or a low altitude source, following a predictable line. Variations off that line may give you an idea of whether that water source was coming from a more humid or a more arid vapor source, or whether any evaporation may have occurred prior to it being recharged into the aquifer systems. So knowing this, we can collect these data and have endpoint members known for typical winter precipitation or typical summer precipitation. Taking springs data, we can put that into a mixing model and get an idea of what the contribution of these seasons are to the ultimate constituents of the aquifers. So the models indicate that the majority of the recharge is occurring as snowmelt. Winter precipitation infiltrating into the aquifer during the springtime. The fraction of the winter recharge, at least at those 3 gauge sites along the south rim, for which we have the largest number of samples, indicates that that's a pretty sizable percentage, running from the high 60s to the high 70%. Interesting as well is that there's a winter signature no matter when the sampling season. If I were to go down to Indian Gardens and take a sample of that spring in July and again in December, both times it would still have a signature indicating winter precipitation. Now, in addition to just the collection of strictly numerical data, Grand Canyon has also recently adopted new inventory protocols to look at the entire spring system rather than just the water coming out of these springs. Now, these protocols were originally developed by Stevens, Springer, and Seda in 2004 for the Park Service. It's since been refined by the Southern Colorado Plateau Network of Parks, part of the National Park Service, as well as Grand Canyon, with a lot of help from Grand Canyon Trust and their volunteers. They've been field tested, more revisions have been done, and ultimately we have a number of different protocols now that can be used brought out into the field depending on how much time we think we'd have at a site, the type of spring, the size, or the complexity, or even the levels of the experience of the folks that would be conducting the investigation. Some of the data that's being collected at these sites include location data and information on geomorphology, hydrology, botany, water quality, as well as other things like repeat photography, site sketches, and botanical collections. And what we can do is start building up a database of this